Before I answer your questions, so let me give you some important information about midterm. We know this is most important in our, because the same percentage as the final, okay, 15%, midterm and both and final. Same weight. All right. First, the first change, big change. So let me write the important information on this file. So later I can upload, and also record it in the video. All right, so this is, I will talk about hints. Okay, First, I like to talk about the midterm. Right, Coverage first, coverage. All right, So based on these 3 assignments, the first one, homework 1, the one you're currently working on. The second, quiz number 1. The third, quiz number 2. And I will not give you quiz number 3 before the midterm. After the midterm, then I'll quickly give you quiz number 3. Okay, because I want you to focus on homework number 1. That is a relatively hard assignment, so give you more time. And these questions will be explained in our review sessions. Yes, you got it. Both Tuesday, Thursday. Because after I move the test date to next weekend, then we can use, but not a full Tuesday, Thursday sessions. Half, okay? Tuesday 1/2, Thursday 1/2.
Will it be open on the weekend or during the week?
We can. All right, so super long weekend. So not, weekend 2 days, right? So I extend a little bit. I extend to Friday, starting Friday, whole Friday, then Saturday, Sunday, and a Monday. Give you 4 days. All right, So let me put here. So let me check. So the online, okay, change to online. Okay, this is important information. Okay, not in classroom, but only this change only for midterm, not for final. Okay, final still here. So midterm, I like you to do well in midterm. Okay, so try your best to get the best grade in midterm. Okay, so 4 days, starting from Friday through Monday. Okay, so that Friday, what is the date? Friday, 14th? Okay, 14th. July 14th. 18th, 5th, 6th, 17th, right? Monday, 17th, right? Yeah. Okay. 4 full days, okay? Yeah, 4 full days. All right. Any questions related to midterm?
Will it be like our quizzes where we present time?
Right, no time limit.
Okay.
You're talking about quiz, right?
Yeah, like, oh, is the midterm gonna be like the quizzes?
Oh, like the, oh, mid,
I'm just curious.
all right, midterm, yeah, more information for the midterm. Midterm, not like quiz, okay? The format, not like quiz, the format like homework assignment. Homework one, homework number
Okay, so-
one, that,
Gonna open it up and you'll have the back.
right? I put it on PDF file. So you download PDF file, okay? You work on it, you know, on paper or software. So you choose the way. Yeah. So the same way as the homework assignment that I do grading. Yeah. So four full days. Midterm. Yeah. Okay. Yeah, but the final will be different. You know, but let's forget about the final. So let's, you know, work on the midterm first. Yeah. Dakota?
So you can kind of like open it, start it on day one. Don't have to split it until.
The end of July 17th, Monday. The end of. Yep, no time limit, no clock, you know.
My God,
Yeah, just,
y'all don't have tears in your eyes?
yeah, someone talking on the Zoom. Yeah. All right, yeah, probably. All right. Okay, yeah. Hope you get this update. Yeah. Any other question? Yeah, too noisy.
Let me go grab, one of the- this is letting off.
Yeah, if you know how to fix that. Yeah, because too much distraction. Yeah, too much distraction. Is it a fan thing or not? Hey, if I turn off the fan, I don't know, air conditioning.
Oh, that's true. Yeah, that's true. Whether or not you
I-
got-
I turn off the fan, is it better?
No, that doesn't change it. It's still on.
All right. Yeah, let's try our best to concentrate. Yeah.
Yeah.
Ask your homework questions. Yeah.
Wait, wasn't there 2 more things? Are you going over anything else with midterm?
Too many, 3 assignments, so you feel too many? Yeah. Yeah.
No, I just meant, was there anything else that you wanted to say about the midterm? Not like.
Yeah. I do not have in my mind. Yeah. So if any of you can, you know, give, yeah, Dakota.
So I guess I either forgot or don't really fully understand this, but when can we say an algorithm is optimal? It's never optimal, right?
Good question. Good question. Yeah. Like this. Only when we can prove rigorously it is optimal, then we can say it's optimal. Remember how we did for the element uniqueness question. Element uniqueness, I think we proved it rigorously. We made convincing arguments. Okay, quite convincing.
So I guess you could say if one person has, over and over again proven it rigorously, then you could say it's optimal. Or do you have to have more than one person?
One person, that's enough. If one person, if the proof is correct, that's enough. Okay, yeah. The whole world, only we need one person who can solve it, then our whole mankind, we share that. Okay, if one person can make it, then we treat all of us can make it. Okay, we treat all of us can make it. Okay, all right, yeah, we will get there when we do the review. Okay, on Tuesday review. All right, yeah.
This is kind of like just a general question. For the questions that have multiple options of the answers, were you wanting like a justification for why?
No, I do not need. Yeah, I do not need. But for multiple questions, there is this kind of possibility. Because some of you sometimes feel probably more than one options make sense. Sometimes you may feel in that way. Yeah, that could happen. For me, I always choose one correct answer in the multiple options, but some of the options could be partially correct. Okay, yeah. In that situation, you pick the best one. If you feel, both looks fine, yeah, but which one better? Pick the best one. The second best, I will give partial credit. Okay, yeah, we could have second best, but you do not get full credit. You just get partial credit. Okay, yeah, always pick the best one.
So you're saying some answers could technically have a very similar to same solution?
Not so, because the answer, yeah. If I have that example, so I can show you, yeah. So some, yeah, it's not a number, two number, you cannot have two, right? Yeah, and actually number you can also have partial credit is if one answer is very close to the correct answer. Yeah, so I may give it partial credit. Okay, yeah, but if far away, yeah, usually I treat how close one difference. Okay, one difference I may give you partial credit. Yeah, if the difference is more than one, then I will not give you a partial credit. Okay, yeah. But for some sentence options, statement options, yeah. Some statement could be better than others. In that case, some statement partially correct. Then I give you 2 points. Yeah, there is a situation I may give you, 4 to 1. Okay, 4 to 1. Second best 2 points. Third best just a little related, 1 point. I just try my best to give you a partial credit. Okay. Yeah. All right. Start your homework question. Question number 2. Yeah. All right. So do you remember there is a similar question in your quiz 2, right? 1, 4, 6. Yeah. So here, there is some hidden knowledge there. All right. So if we go back to quiz question number 2, yeah, I do not remember which one, but the polynomial is 1 plus 4x plus 6x squared plus 4x cubed plus x to the 4th. Here, these coefficients, is any of you, if you have knowledge about the coefficients, some special pattern? Have you noticed special pattern of the coefficients here? Yeah, most of you may not. So here, let me remind you the special pattern called Pascal's triangle. Pascal's triangle. So what's that? All right. You consider 1 plus x to the nth power. Binomial expansion, binomial, okay? Yeah, binomial expansion, all right. Yeah, sometimes people write a plus b to the nth power. Yeah, but here, let me use the simple example of this. When n equals 0, you get a 1, okay? When n equals 1, you get two coefficients. That's 1, 1. Okay? You have, this is, we start drawing Pascal's triangle. Okay? Then when n equals 2, 1 here, the number 2, you add up the two numbers of the shoulder, you get 2 and 1 here. Yeah, because you only get one number you can use. N equals 3, 1, 3, 3, 1. Okay, adding up these two numbers. Okay, then 1, 4, 6, 4, 1, and so on. Here, the one we need here, 1, 5, 10, 10, 5, 1. Okay, yeah. So that's the pattern for Pascal's triangle. Okay, after if you can identify it, you need to be aware of it. You need to be sensitive to the coefficients following the Pascal's triangle pattern. Okay, if you have this knowledge, this is critical piece of knowledge. If you have this knowledge, then you can write it as 1 plus x to the 5th. To the 5th. How about that? Okay. You write in this format. 1 plus x parenthesis to the 5th. And here I ask you to count minimum number of multiplications. We do not count addition. Okay. 1 plus x inside parenthesis doesn't matter because nothing to do with multiplication, right? Yeah. So one addition inside parenthesis. After we get this whole number, 1 plus x, then how do we raise to 5th power quickly? The best way. Raise to 5th power quickly. Okay. Yeah. For our quiz question, 1 plus x to the 4th. How can we get the 4th power quickly? Quickly. That means the minimum number of multiplications. We want to get 4th power. Okay. Yeah.
Horner's rule?
Horner's rule, not that fast. Horner's rule, 4th power, you need 3 multiplications. 5th power, you need a 4th multiplication. We have another way we can do faster than Horner's rule. Faster. Yeah, let me show you. Okay. Yeah. So you missed that part. 1 plus x squared, that's 1 multiplication, right? Yeah. We do 1 multiplication, we get 1 plus x squared. Then next one, because we already have the answer for 1 plus x whole thing squared, when we move to 4th power, can we take another square on 1 plus x square? How about that? Square of square. Another multiplication, we get the 4th power. How about that? Oh, sorry. Yeah, I can erase it. Yeah, I saw some of you feel strange. Yeah. How about this square? Yeah, because we already have this number. We just take another square on this result number. Okay. Then to the fourth, we only need 2 multiplications, right? How about that? 2 multiplications. For Horner's rule, you need 3 multiplications. This way, we reduce that number 2 multiplications. How about that? Think about the trick. This trick, clever trick. Okay, we call it repeated squaring technique. Yeah. So this method we called repeated squaring. Technique. Okay. Okay. Yeah, but in order to apply this repeated squaring technique, you need something to certain power function. Okay. Yeah. So you need to get a power function. Okay. Yeah. Something to the certain power. Okay. Yeah. All right. For your homework question, 5th power. Can you do a little faster? 5th power. Okay. Better than Horner's rule. You get 5th power. Right? Yeah. All right. So you need to figure out. It's very close. With this knowledge, you need 2 pieces of knowledge to answer this question. Well, Pascal's triangle first, repeated squaring technique second. After these 2 pieces, knowledge equipped, you can figure out. Okay. Yeah. Try to understand the smart way here. Yeah. Let me push another. Yeah. If raised to 8th power, you just need another multiplication, right? Square of 4th power. Square of 4th power, you get 8th power, right? If I ask you 16th power, then square of 8th power, you get a 16th power, right? Think about that. You will move very fast. Okay, yeah. Now, let me ask you, if we want to calculate 1 plus x raised to 1024th power, how many multiplications do we need? The minimum number of multiplications we need. Power of 2. The exponent number, power of 2. Get the rule? Rule. Some rule. When n, so here, when n is a power of 2, we can apply repeated squaring technique to get a minimum number of multiplications. Yeah. 1 plus x square, 1 multiplication. 2 to the first. Yeah. So let's find the rule. 1 plus x square, that means exponent number is 2. That's 2 to the first. You need a 1 multiplication, right? Yeah. 1 plus x to the 4th, that's 2 square. Exponent number, you need 2 multiplications, right? Yeah. 8, 2 to the 3rd, you need 3 multiplications, right? Can you get the rule, right? And here, 1024, we know that's 2 to the 10th power, right? 2 to the 10th. So when n equals 2 to the 10th, how many multiplications do we need? 10. Right? Is it much better than Horner's rule? Horner's rule, look at that, Horner's rule. Horner's rule, we need 2, 3. Huge difference, right? 10 versus 1023. Huge difference, right? See? Huge difference. Horner's rule. Yeah.
So that's because we're doing like the additions on the inside and just like almost just taking the exponent of that number on the inside.
Yes. We do not consider addition. Yeah. Because too little comparing with multiplication 1/10, right? The cost. You know, too little. Yeah. So we do not worry about that. Yeah. So then when you raise to certain power, jump as fast as you can, double, double, double. Yeah. Each multiplication, you double the exponent. You double the exponent every multiplication.
I guess what I'm mainly asking is the only reason we're able to apply such a rule is because of Pascal's triangle. If it wasn't for the triangle, we wouldn't be able to apply it.
That's another thing. All right. Yeah. So 2 separate things. To apply this repeated squaring, we need the exponent number power of 2. Okay. But if it's not exactly power of 2, number 5. 5 is not exactly power of 2. But it's close to power of 2, right? 4. After we get 4, one more multiplication, we can get 5, right? Yeah. Yeah. So we try to get the closest power of 2. Then we try to do the extra. Yeah, we need to do some extra work. Okay. Yeah. But for the Pascal's triangle, the goal, we want to get a power function. If you do not apply Pascal, so you get a regular polynomial. It's not a power function, right? Yeah. It's just a polynomial. Okay. Yeah. But this repeated squaring technique we cannot apply on arbitrary polynomial. Okay. Only the special, only the monomial, okay, single term monomial we can apply, but not on polynomial. Okay. Yeah. Monomial case we can apply. Okay. All right. Yeah. Hope you get it. Yeah. You get it. Yeah. This technique is very important. Yeah. Try to understand. And whenever you have a chance, you need to apply this technique. Okay. Yeah. Yeah. We will have further discussion in our review sessions. So I will try to do some more examples, okay, to let you practice. Yeah, because it's important. Yeah. So I will give you this kind of questions in the midterm. Okay. So you need to completely understand this technique. Okay. Yeah. Pascal's triangle, so you can search the web, you can find it easily. Yeah. Or you know the rule, you can write on a piece of paper, you generate easily. Okay. Yeah. All right, next question. Number 15. All right. Yeah, okay. Number 15. Yeah. So here, yeah, actually, yeah, this is number 15. I need to give you, yeah, so I need to give you a formula for this, yeah, this question. Yeah. All right. For tower of Hanoi problem, okay, yeah. N disks, given N disks, then the number of moves equals 2 to the n minus 1. Okay. The number of moves you solve the Pascal's triangle using our recursive algorithm, you will get this number of moves, 2 to the n minus 1. Okay. Yeah. For example, okay, we did n equals 3, right? We did n, yeah, so slow. We did a 3, n equals 3 case. Remember, we need 7 moves. Okay, we need 7 moves. Yeah. Example, e.g., e dot g dot. Yeah, e dot g dot, e.g. example. Okay, yeah. So 2 to the third minus 1 equals 7. The formula. Okay, yeah. Yeah, why is that? Yeah, why is that actually here? I can show you a little bit. Yeah, actually, I plan to explain this in my PowerPoint slides. Yeah, but so here we can get a recurrence equation here. Yeah, remember when we need to. Yeah, so here let's recall how do we do the recurrence relation? That procedure. Let's recall that procedure. Recurrence relation. Okay, when we solve the P of n, we need to, yeah, so here, when we solve the P of n, we need to, the first step, we need to do P of n minus 1 first, okay? After that, we need to make one move. Remember the bottom disk, move that largest bottom disk to the destination pad, okay? After that, we need to do another P of n minus 1. Okay, yeah. All right. Based on this recurrence relation, let's consider the number of moves. Let's count the number of moves for n disk, C of n function. C of n function, in order to get a C of n function, counting this many moves, we need to do n minus 1 disk problem twice. That means 2 times C of n minus 1. Okay. Yeah, it's too slow here today. Yeah, C times 2 times C of n minus 1 plus a constant number 1. One move, bottom disk, one move. Okay, that means we need to solve this recurrence relation. Solving this recurrence relation. Okay, yeah. Here, let me show you how to solve. there is a smart trick we can apply to solve this recurrence relation. Do subtraction both sides by 1. Let me see. Oh, not subtraction, addition. Do addition both sides by 1. Why? You may ask me why. Yeah. So because we got, so our goal, why we do this transformation, we want to make both sides have the similar structure. Equation, both sides, we want them have similar structure. So by adding 1 both sides, left-hand side will be C of n plus 1. Right-hand side will be 2 times C of n minus 1 plus 2, right? Plus 2, we can factor that 2 common factor out. C of n minus 1 plus 1. Okay? Why we do this? Why we do this transformation? The reason is simple. The reason is we want to make the left-hand side structure C function plus 1. Right-hand side inside the brackets, the structure, they have similar structure. How about that? Similarity. We explore the similarity structure both sides. Okay? Yeah. Because this kind of structure similar, can we use a new function d of n to replace this C of n function? Yeah. Yeah. D function equals 2 times d of n minus 1 function. How about that? We use that C of n plus 1. We do substitution. This whole thing, we use a new function, d function, d of 1 to replace it. The reason is this d version looks simpler than C version, right? Constant is gone. All the constant numbers all gone. Okay? We only d of n equals 2 times d of n minus 1. Okay? Yeah. Can we apply this recurrence relation another time? 2 squared times d of n minus 2. And so on. Can we keep doing this again and again? Keep doing this again and again. Okay? Dot, dot, dot. Until we get a power, kth power, 2 to the k times d of n minus what? 2 to the k, if we do this recurrence relation multiple times, 2 to the k times d of n minus k. Yep, because 2 to the first, d n minus 1. 2 squared d n minus 2. 2 to the k d n minus k. How about that? Okay, yeah. Then when we move to the last one, 2 to the n minus 1. How about that? 2 to the n minus 1 d of 1. How about that? D of 1. N minus 1 plus 1 invariant n. Here we use the invariant n. Invariant idea. N minus 1 plus 1 equals n. N is our invariant. We use invariant n to keep track of all the terms, all the steps. Okay, keep track of all the steps. K plus n minus k, that's n invariant. N invariant. Okay, yeah, here. So the last one, 2 to the n minus 1 times d of 1. What is d of 1? D of 1. Yeah, because d of 1 equals C of 1 plus 1, right? What is C of 1? One disk, how many moves you make for one disk? One move, right? 1 to the destination, 1 move. So C of 1 is 1, 1 plus 1 is 2. That means D of 1 equals 2. Okay, 2 times 2 to the n minus 1, you get a 2 to the nth power. So the D function equals 2 to the n. How about C function? C function just the D function minus 1. Okay, C of n equals 2 to the n minus 1. Okay, yeah, so that's the formula I gave you before. Here, I show you how to find the answer. We do n minus 1 twice. Yes, yes. Yes, yes. Yeah. Yeah. Just recall. Also recall our pseudocode. We do recurrence call twice, right? At the beginning, once, then we make a middle move. Then after that, we move to another time, n minus 1 twice. Yeah. So we have that too, coefficient 2. Okay. Yeah. So that reason. Now, think about for this question, if you can apply this formula directly, now you can apply 2 to the n minus 1. Yeah. So m1 disk 2 to the m1 minus 1, that's the number of moves, right? m2, 2 to the m2 minus 1, that's the number of moves. You can use that formula, right? Yes, and try to figure out what is little m1, little m2. With this formula, try to figure out. Little m1, little m2. Oh, you solve the problem after you go home. Yeah, you're not here, not solving here. Yeah, think about. Yeah, I just ask you to think about. Connect. After you get this formula, it should not be that hard. Okay. Yeah. Other questions? Other questions?
For that next one, is there a pattern in those terms? Like, how do we know how many terms are for 16?
Oh, no, 6. Oh, yeah, yeah. Do your observation. Yeah. All right. So question number 16. I like you to do counting by reference. Okay. Remember, I introduced a counting technique, counting by reference. All right. But when you do that, each plus sign, can you associate with some subscript, superscript, or subscript? Okay. Yeah. One plus sign associated with its most closest subscript. Okay. Yeah. So the first plus sign associated with the first. Yeah. Okay. Yeah. First plus sign associated with subscript or superscript 5. Second associated with 8. Third associated with 11, and so on. Okay. All right. Right, right. The last one associated with that 302. Here, counting these, now you need to count the number of subscripts, but they are not consecutive numbers, right? Yeah. Can you figure out the pattern? Some pattern? Can you use the pattern you find to count the number of subscripts? That's the goal. Okay. Yeah. count the number of subscripts. That's exactly the number of addition plus signs. Counting by reference, the practice in this way. Yeah. Okay, yeah. Next question.
Way to compare the growth rates of functions with the same, like, dominant term.
Growth rate, same function.
Yeah, so like,
Number 11.
I'm specific.
Yeah, number 11.
Like number 11.
All right, yeah. Dominant term. We focus on dominant term. So non-dominant term, we can safely erase. For example, this one, non-dominant term, we can erase it. Okay, yeah, all right. So dominant term. But for the dominant term, there is another part I like to, make your thinking going that way. Yeah, that is, remember, we introduced the concept called order of growth. Order of growth concept. Here the question, what's the order of growth, right? Let me give you the specific number order of growth. Yeah. All right. For n squared, order of growth is this 2. N to the certain exponent, that number we call order of growth. Okay. Yeah. And 1. Order of growth 1. All right. This is hard. Yeah, this is a hard one. All right. Yeah. This is hard one. Okay. Log. The question is, what is order of growth of log? That's hard to answer. Okay. Yeah. Yeah. All right. So here, the reason is this. When you have a function, power function, the order of growth is easy. Power function n to the dth power. So then the order of growth d, order of growth. Okay, straightforward. But if for non-power function, it's hard. Exponential function, log function, then it's hard. Okay, yeah. So for your thinking, in calculus, epsilon delta language, right? You know a little regarding epsilon delta language in calculus when we, yeah, epsilon delta language, okay, yeah. So, yeah, so here I do not go completely that kind of language, but I want to borrow that epsilon concept here. Borrow it, epsilon concept. You know epsilon, right? Epsilon, very special symbol. Okay, yeah. We can make it very small, right? Arbitrarily small, epsilon. Okay, here I want to borrow that epsilon notation. So log of n, we can treat it as n to the epsilon. N to the epsilon. But what's the epsilon? This epsilon, we treat it as greater than 0. Epsilon must be a positive number. It cannot be 0. Okay? But less than any positive number d. Whatever positive number you make d, epsilon is smaller than that. 0.0, many 100 zeros for d, our epsilon is still smaller than that. You use this epsilon for your thinking, okay? For your thinking. Now when you do comparison, this one you can use n to the epsilon. That one you can use 1 plus epsilon, right? Because 1 times log, 1 plus epsilon. And now you can compare the order of growth, right? The first one is 1, second one epsilon, third one is 1 plus epsilon, fourth one is 2. You can do comparisons, right? Yeah. For number 11, can you do simplification first? N squared take square root. Okay, so that's n to the first, order of growth 1, right? Yeah. Here, this is very large. Okay, exponential function, you know how large. Okay, here for me, yeah, for me it's hard to, yeah, we infinity, but infinity, yeah, the order could, yeah, you can think of infinity. Okay, the order, yeah, because when you compare, that order is greater than any positive number. Any positive number. Right. Factorial is, you know, close to e to the nth power. Yeah, close to. Okay. Yeah. So we can connect to it. Connect to it. Yeah, factorial. All right. So this one, C, you can use that epsilon. Is it 1 minus epsilon? Because log at the denominator, right? Can you do 1 minus epsilon? Okay. Yeah. So this, we cross out log because plus, right? Plus we can cross out. Okay. So n to the first. Can you do comparison? Can you do comparison? Right? Think about that. Order of growth. Order of growth. Yeah. Try to use epsilon, but this epsilon has the special property. This is special property. A little abstract. Yeah. A little abstract. But we need some abstraction. Yeah. We need to use some abstraction. Yeah. All right. Number 12, similar, right? Yeah, number 12, you can use the similar way to answer number 12 question. Yeah.
I see it now.
Yeah, you see it, right? Now you can do comparison A and B. You use epsilon. Epsilon. Okay. Yeah. All right. Next question. Next question. It's fine. It's 21. Yeah, because everyone benefits from the,
Yeah.
right, answers. Yeah. Number 21, given an array with n greater than 3 elements, we can apply one swap operation on arbitrary 2 elements. What is the minimum number of inversions? Or maximum, yeah, correct, maximum number of inversions that can be reduced by one swap operation. Okay, yeah, one swap. Yeah. First, you need to get an idea. All right, so maximum number of inversions. So we just swap 2 of them. All right. First, this one is very hard. Yeah, this one is very hard. First, you need to consider locations of these 2 elements to be swapped. Okay, locations. Think about if the locations matter or not. The locations related to the maximum number or not. Think about that. Yes. Let me draw this array. Okay, array. Yeah. Array. So all the elements we distribute along this array. Okay, all right. Now I pick two of the elements I want to do swap operation. Okay. A sub I and A sub j. We do swap operation. Okay. Now let's consider the impact of the swap operation in our counting number of inversions. When we count number of inversions, the swap operation make any change to the count number. When we count number inversions, this will make any change. Think about that question. All right. Yeah. These two elements divide the whole array into 3 line segments, right? Three parts. Part 1, okay? Yeah. Part 2 and part 3. Okay, all right. So when you do swap operation, look at so here, when you consider one inversion, look at your, yeah, so here, inversion. So now we consider inversion. Okay. For the number of inversion, we need to consider 2 elements, right? 2 elements, okay? Yeah. So inversion a to the x, a sub x and a sub y. How about that? A sub x, a sub y. Look at if they form inversion. Okay, all right. Think about if a sub x is here, a sub y is there. When we do swap between ai, aj, does it impact this inversion? No, right? Doesn't matter, right? Doesn't matter, right? Think about, so when a sub x in region 1, a sub y in region 3, before that swap, after that swap, this pair, if it is an inversion or not, the answer is the same, right? Yeah, when we do this swap operation, we do not change the counting on this pair, right? Inversion counting on this pair. We do not change that counting, okay? That means no impact, right? When we do swap, that means no impact, okay? Yeah. Elements at the left-hand side, at the right-hand side, right? Think about that, okay? All right. Then elements, think about in different portions, elements in different portions. Which one you may have impact? Think about that. Which one you may have impact? When only when ax or ay is one of ai or aj, right? Yeah, only when you touch it, then you have impact, right? If you do not touch it, you have no impact, right? Think about that. Okay. Yeah. So that's one thing. Yeah. All right. Another thing. All right. So here, this tells us when you count inversion, Here we count inversion change. All right. Because our goal, so here we count inversion change. Or to right. Count the inversion change. You only inversion change. If no change, we ignore it. If no change, we ignore it. Okay. Inversion change, you only consider the pairs A. Too bad. Why so slow? A sub I A right. A sub X or right. A sub J for the inversion change, you only consider these two types, right? Yeah. These two types. Okay. Yeah. All right. Now look at this one. I only need to do analysis on this one. For AX. All right. So AS, you need to consider three regions, right? Region 1, region 2, region 3. AX sub X comes from three different positions, different types of positions. Okay, yeah. Where AX comes from region 1, is there any change before swap, after swap? No change, right? When AX comes from region 2, is there any change before swap, after swap? Region 2. Region 2. Before change, after. Yeah, could be changed. All right, region 2. How about region 3? When AX comes from region 3, any change? Any change before swap? Region 3. Region 3. Inversion, no change, right? So you can see region 1, no change. Region 3, no change. Only region 2, you have the change. So this analysis tells you what conclusion you can get. This analysis. What conclusion you can get? We want to get a maximum number of inversions, right? We want to get maximum. Maximum, we want to make the change as big as possible, right? That means we should compress region 1, region 3. How about that? We should compress region 1, region 3. That means we should enlarge region 2 as big as possible. Region 2 as big as possible. Okay? Yeah. How to make region 2 the maximum? Region 2 maximum. That means the whole line segment, except the first one, last one, all the other elements belong to region 2. No region 1, no region 3. That's the largest possible region 2. Okay, we can make the change the biggest. All right, now you consider this case. Swap first element, last element to get the maximum number of inversions. First and the last to get a maximum inversions. Now you're halfway there. You only consider first and the last. Swap to get the biggest change, inversion change.
Is inversion mean that like two elements are out of order?
Yes.
Okay.
Yep. Out of order.
That's globally, not just.
Globally. Yeah. Globally.
So just not- it's not what we-
Yes. Globally. Yeah. Yeah. Globally. Globally.
The maximum number of elements out of order globally is.
Well, that helps.
Now, yeah, only consider, yeah. Oh, yeah, this way. You use n consecutive numbers. Okay, you use n consecutive numbers, 1, 2, 3, through n. For that n, you can choose some certain numbers. Okay, try to figure out the first one, last one, swap. Okay, yeah, and try to guess the formula. Make a guess. Okay, you can apply guess and verify. How about that? Guess some formula, then verify. Use some more examples to verify it.
So basically, you get more inversions when you don't swap it with a.
Do you want, yeah, do you want me to give you a little more information? Yeah, like this. Okay, all right. How about let's use simple examples. 1, 2, 3. How about that?
Okay.
1, 2, 3. Before swap. Okay. Then we do swap. We swap 1 and 3. Okay. 3, 2, 1. Right. All right. Now you count the number of inversions change. They change. All right. Yeah. Before swap, how many inversions do you have? 0. Yeah, 0. No inversions. All pairs are in order. Okay. Yeah. After inversions, how many? After swap, how many inversions?
I think that you have to, so it's the global ones for each of them, right? So 3 is out of order, 1 and 2, because it's at the front and it's the last.
Right.
So it's how many other elements, and so it's 2 for each of them, so.
All right, let's count in this way. All right, let's pick the first one, 3 element. 3, 2, is it inversion? 3, 2,
Yes, the
Yes.
global inversion.
yeah. 3, 1 inversion.
Yes, it's global.
Number 2, yeah, global, yeah, whatever. 2, 1 inversion. Yeah, that's 3. That's all we have, right? No more.
Oh, we only count them once.
Yeah, only count
Okay.
once. Yeah. Only count once. Each pair only count once. 3. The
Fine.
change 3. Yeah,
Fine.
that's for n equals 3. Then you can try n equals 4, equals 5. Yeah. And see, try to figure out certain formula. Okay. Try to guess. Formula related to n in terms of n. Yeah. Yeah, we don't know. We need to guess by our experiments. We make a guess. Okay. We have experiment here. So we make that guess. Yeah. So then After you guess that formula, use that one to verify a few more examples. Okay, and make sure your guess is correct. Okay, yeah. Yeah. Try this way. All right. Yeah. Yeah. Okay. Yeah. All right. Another question. Yeah, here we already passed but another question, then we take a break. How about that? Yeah. Another question when we get 7 o'clock, let's take a break. Let's get one more for the break first. All right.
Okay.
Yeah.
Because I was just had a question about number 6. I was just it's a clarifying question, but it has to do with, so I was gonna just ask, what do you mean by even number of units squared?
All right. 2 by 2, 2 times 2, that 4 squares, that even number.
Okay,
3 by 3, that's odd number.
okay.
Yep.
So as long as it's even number.
Yes,
So-
as long as
Okay.
even number. Yeah. As long as even.
Yeah, so
We
you're
do-
supposed to keep them even.
Right. We do not count. Another question. We still have time before the break. We have another time for another question.
Thank you.
All right. Yeah. 4-element array. Find both maximum and minimum. How many comparisons? We want to use minimum number of comparisons to answer this question for the worst case. All right, for the worst case. Okay, but minimum number of comparisons. All right. So here, all right. When you think about it, yeah, using that elimination method idea, okay? Yes. When you think, we learned that elimination method. Why so hard to erase? Yeah. All right. Elimination method. Okay. Yeah. What do you mean here, elimination method? All right. So here, let me show you the elimination thinking here. Okay. All right. Let's do arbitrary comparison. We need to do at least one comparison. Right? Think about that. We need to do at least one comparison. Let's do one comparison, x1, x2, and we can assume x1 less than x2. Just one less than another. So it's, not important which one larger, smaller. We just assume after one comparison, we get x1 less than x2. What conclusion can you make? x1 less than x2. When we consider minimum, can we eliminate x1? Oh, sorry, yeah, maximum, right? x1 cannot be maximum, right? Yeah. So after one comparison, we can get x1. Sorry, yeah. Too slow. Oh. X1 not equal to max. Okay. Can we get x, also x2 cannot be the minimum? All right. So one comparison, we can get that. All right. All right. So assume we do another comparison, x3 less than x4. All right. After the second comparison, we can get X3 cannot be maximum. And X4, sorry, yeah. Too slow. X, okay. All right. X4 cannot be minimum. Look at that. Okay. Here we do two comparisons. After two comparisons, we can get this much information. Some elements cannot be maximum, some elements cannot be minimum. Unordered, yeah, unordered. But here, you may ask me why I can assume these two. Because, oh, another thing, we assume also distinct. Do not consider equal case, yeah, for simplicity, yeah, distinct, okay, all right. Then one must be less than another, right? Yeah, one is smaller. It's not important we call one x1, x2, right? We just for convenience, we make smaller one x1, larger one x2, you know, yeah, one smaller, one larger, but it consumes one comparison. After one comparison, you know, one smaller, another larger. That's all we need. Okay, all right. After that, the next round, here we treat as the first round processing. Okay, first we get a partial information. The next round, when you look for minimum, you can ignore those eliminated, right? Yeah, elimination. Some elements can be eliminated for minimum. Okay, yeah. Some of the elements can be eliminated for maximum. Elimination methods, right? Yeah. Go that direction. So you will be, you know, pretty much there. Yeah, pretty much there. Elimination method practice. Okay. Yeah. All right. Yeah. I think we need to take a 15-minute break. Yeah.